Also, in your computer, log into Seneca. Oh, let me actually say, I'm going to bring it up later because I have to add it. Give me just a second. We are section B, correct? We are section B and yes. Yeah, so make sure you have the attendance in front of you, so when I tell you do the attendance, do the attendance. You know, the drill, right? Okay, so I'm going to quickly go through the last lecture that we hadn't completed today, and hopefully it's going to be a short session. It's not going to be a long one. Beforehand, anything, actually I wanted to say any questions about the last lecture, because I'm going to go over everything anyway. If there's any part that you have a problem with, let me know. Next thing, as usual, cell phones, please don't look at them. Put it aside and don't look at them. Don't look at the messages and stuff like that. And again, pay attention to the class and not your screens. Can you see anything? You can change your seat if you want with you. Please sit somewhere else. I feel bad over there. I feel like you have to kind of peek through the screen. Sit somewhere else. Thank you. Thank you. Take your stuff. I'll wait. Doesn't matter. This is kind of awkward because it comes up and then blocks literally exactly where you were sitting. So we started last session by giving you an example of a data entry function that we have written to receive a foolproof data entry for an integer. And let me find my mouse. There you go. The furthest person to the screen, can you see? Is it big enough, or you want me to make the font bigger? Is it okay? And back there, they don't even hear me. You good? You can see it? Everything's good? Okay. So what we did, we created a foolproof data and integer entry function. And we said that it looks fine and dandy. The only problem that it has, it gets a foolproof data, but if I want to customize the data to be a specific value for that, I have to do a function call for that. And because the function call is not changeable, every single time I want to do another type of validation over here, I have to change the name of the function and recompile the code. And that wasn't good. So we said we need to fix this problem. And then we went to the next part that was mentioning that, is this the right one? Yeah. So mentioning that, like arrays, that the name of the array points to a piece of memory for the data, functions work the same way, which the name of the function points to the address of the logic in memory. So wherever the code is in memory, that binary code is in memory, the name of the function holds the address to that data. Therefore, if I print the name of the function only without the function call operator in front of it, so the function call operator in front of the function are the parentheses. When you put the parentheses in front of any pointer, believe me, it wants to call it. Create an integer pointer and put parentheses in front of it, you're going to get an error that you're trying to call something that is not a piece of code. So it tells you that. So that parentheses that you put in front of the name of the function essentially tells to the system, to the C++ language, to jump to that address and start executing. So we said that signature of a function essentially dictates what type of the address the function is pointing to. And we said to create a function, to create a pointer capable of holding the address of a function, I need to exactly write the prototype of the function, line 17 as you see over here. Then put the name of the variable inside parentheses and add an asterisk. That tells to the compiler this is not a function prototype, but it's a pointer who's capable to hold the address of any function with such signature, which is receiving 2 integers and returning a void. Got it? Therefore, now that is a variable. It's not a function. It's a function pointer variable. Therefore, I can put the address of any function to it, and using that indirectly call that function. So line number 21 will call sum because funcPTR is set to sum. Line number 23 will call prod because it's holding prod. And line number 24 will call repeat because it's pointed to repeat. 25. If you look at the function calls, they're all identical. And people, this is not polymorphism. Okay, this is just low-level C programming language. Because no signature is changed, nothing is changed. They're identical. But because the name of the function is a pointer, it jumps to where the logic is pointing to. Are we clear with this? Okay, now having this, we fixed the problem for our function. We said that instead of just having a function that doesn't receive anything, I can pass it a general a pointer to a function that a general validation requires to have, which is essentially receive an integer to validate, returning a Boolean to say if it's valid or not. And we pass that, we ask that anybody who wants to use getInteger pass that function to it. Inside getInt, instead of instead of calling the validation function, I make a call to the pointer to the function. Therefore, whatever is provided to integer, that's going to be the validation function that's going to be called. The first one is going to be adult. The second is adult. The second one is going to be valid number of students. Therefore, the problem is solved. Now I can pass logic to any function I want and make the behavior of my function different. One problem with this is not object-oriented. This is horrible. Using something like this is against every, like it's literally you're writing assembly language here, because you're literally holding the address of where the logic is and tell to CPU to jump to it. So it is completely non-object-oriented. So we don't like it. We like it if it's C, but in C++ we don't do this. Why we don't do this? Because these functions are standalone and they can be called by someone else. Therefore, we don't want them to be passed around or the address is being passed. Okay? We like methods to be inside objects. That's what object orientation is. Later, we'll see that C++ fixes this problem too. You can still use this system if the functions are not a global function. If they are a temporary small little function that you're just going to have it now and evaporates, you can do it. Small logics you can use. We're going to come to it soon. But this we're not going to use. Then what did we say? Oh, and then we mentioned that we can actually make these, now that we know this function to pointers, we can actually extend it to whatever we want. So the getInt function that we have, we can say not only you're supposed to validate the integer, but also you need to set the error message if this thing is not right. So you can request for more stuff to be done in your function pointer, and that makes your validation function diverse. It can do many different things and doing everything properly the way it's supposed to, the way it's supposed to do. After this, we talked about the fact that the function pointer is just a variable, because you are creating a variable, any variable can be an array. Since it can be an array, you can create an array of function pointers and put the address of 5 different things in it and loop through it over and over. And we mentioned that you can do this instead of using a switch statement. This is another way to go faster through things. So instead of writing a switch statement, say select 1 to do this, enter 2 to do this, and switch around, you can simply receive the index of what is supposed to be done and call the function that is associated to it. It's much faster, much, much faster than a switch statement. Then we said, what is the purpose of a pointer to a function? Why do I have a pointer to a function? To pass logic from one place to another place so it can be reused. We already have a mechanism for that in C++. It's called a class. We encapsulate methods in classes so we can pass them around. The thing is that in C++, we said object orientation is to define an object that exists in real world and convert it to a class. So I have a water bottle, the type is thermos, the diameter of the, I don't know, opening is this much, it's insulated. So I put all the things that I want inside this and I make a class in C++. That is not this, it's a different thing. An object that you create in object orientation, it impersonates an object. When you are saying a transcript object is a complicated thing with properties and actions that performs what a transcript is supposed to do in real life. We understand that? A functor is exactly a class that its purpose is to carry a function. That's why they call it functor. So they are using the capability of the class and specialize the class to carry one logic around. That's why the focus of a functor is overloading the function call operator. So essentially you create a class and you name the class usually the name of what it's supposed to do, capitalized, because functions are never capitalized. Functions always start with lowercase. Classes start with uppercase. So now I create a class called add, then I overload the function call operator to do the add thingy. Now I instantiate the class and apply to the instance of the class the function call. Why am I? Oh, yeah, this, sorry. This actually is the second one that I did, the casting. But anyways, I can actually call the function call any way I want. The good thing is that you've done web programming, right? You know, like, what is the difference between a web application and a regular application that you have on a computer? They told you that, right? One is stateless, the other one is stateful. You know what's the difference between? Everybody's laughing. Okay. A web page. Okay, you click on submit, it goes to the server. Okay, it comes back, it forgets what happened. You have to have cookies in there. You have to have hidden values in there. You have to jump through hoops to remember between page to page what happened. Because each submission of the page is a separate execution that is not aware of the other one. So essentially, each submission that you do on a web application, it goes to a server, something gets executed, and come back. Because of that, two separate, it's like you have a program that you executed twice. The first execution is not aware of the second execution unless you create a file or something on a hard drive to remember what happened before. That's what functions are in languages. When a function is called, it goes back, you call the function again, it doesn't remember what happened last time unless you have some kind of a global variable or some kind of or it's a method of a class that remembers what's going on, right? This solves the problem with that. Functors, because they are classes, you can actually have attributes. So every time the function is called, you can remember things from its last execution. It can have a common attribute between function calls. So you not only have a function call, like if I have a validation function, I can actually have number of tries to make sure more than 3 times they are not entering their password, for example. You can do stuff like that. You can't do it with a regular function. With the regular function, you have to create a variable, pass it to a function, make it global, whatever, okay? So with this one, it gives state to your function call. So your functor, unlike regular functions, is stateful. You can add properties, you can remember things in it, okay? But it gets called exactly like a function. And yeah, it works like that. And that's what the beauty of it. Now, how do we actually manage to make a functor being like in the other one, other validation, the shared, the common thing between the pointers were the signature of the functions. We said that any function with this signature can be passed. In object orientation, we don't have that. Although now our functor function is inside an object, I can pass the add around and the function goes with it, right? I don't need to pass the address anymore. I pass the variable, and because this variable add has the function in it, the function goes with it. I don't need to pass any address anymore. The only problem over here is that how do I make something to have a common signature like functions. In functions, I'll say all validations, they accept an integer and return a Boolean. This is a functor. If I want to pass it, I'm going to say pass the add. How do I do that? That is done with inheritance. In here, it's done with inheritance. If you want to do validation, you create a master validator class, an abstract-based class, then you inherit all your functors for validation from that. Now, your validation function receives the base class. Because it receives base class, you can pass any child to it, therefore the diversity that we have for the things. We'll come to it soon, I'll explain. Okay? So that's that. So that's functors. And we said, and this is, I should have mentioned this before functors. Shoot! I'm a bad person. Go back to your pointer to functions, okay? Pointer to functions are simply functions, right? If you can make a function template, you can make a pointer to a function template too. None. Don't give it extra credit. Like in here for the sort thingy, I am passing a pointer to a function to make it ascending or descending. So now I can make that compare thingy a template too. So some faces look like question mark. Okay, so the sort, let me take this thing away. I should have mentioned this before the functors. I'm so sorry. So the sort method of mine is doing ascending and descending by changing the comparison function. So if the ascending is ascending greater than, it will be ascending. If its comparison returns true when it's less than, then it becomes descending. So ascending and descending is done that way. Now, if I want my sort to be able to sort any type of array, cars, students, driver's licenses, social insurance cards, OOP numbers, whatever, each one has its own specification with less than and greater than. So if I want to do that, to make the template, I'm going to make the array type template, and I'm going to say the two things that are passed to the comparison function is templated too. Therefore, if they create an ascending between two cars, say based on the driver's license, they're going to do this. So depending on what is the function template is implemented for, it can be used. Essentially what I'm saying is that if when you make a function pointer templated, it means if I want to sort cars, there should be a function for two cars to be compared and return a Boolean. Done. So if they implement that, this will work for that one too. As easy as that. Then we talked about, what did we talk about? We talked about the auto return type and really not important. Yeah, I just wanted to say auto return type and trailing things. This is not a good example for it. Did I have this one over here? Yeah. Yeah, auto and trailing types. We said that auto is essentially to, you can use auto for functions too, since the focus of our discussion is functions. If you use auto for return type, either it will decide of the type of the function by the return value of the function, or by the trailing, you can override it by the trailing return type. So essentially, you can actually say, I want my get constant to return a ticket type. So therefore, it knows it's going to return it. So if you are writing a prototype, you have to write this. But if you are writing the function itself, this was not needed. You don't need to do this. This essentially means that because it's returning a ticket type, automatically it will return a ticket type. Okay? So if you have the return statement, it can actually find out what it is. And if not, that's that. Okay, Control Z, we go over there. And why we need auto and trailing space? That's because I said when you're using templates sometimes based on the arguments that you are creating for your templates or things that are happening, the return type of the template may need to change. And we couldn't have done that if we had just the regular return type over here, because then you had to decide what you want to do. To make that happen, compiler needs to first know what the arguments are and then based on that decide what the return type is. That's why we have trailing return type. The trailing return type says, see what is the outcome of this operation, give me that type, now make the return type to be that. Therefore, the return type becomes templated too. If compiler always goes from left to right? If I had over here double add, yada, yada, or whatever, if I say t add, it first compiles this, then reaches over here. Then it cannot change that based on what it has over here. It's too late. It's already compiled, okay? Because of that, it's going to write. And that's the reason for that. Talking about functions, we said that we add a prototype to make a function global everywhere, to be able to be accessible throughout the modules. We can do the exact opposite by making a function static. So if you make a function static, it means it becomes internal linkage, exactly like a variable. If you make a global variable inside the file and make it static, it means it cannot be externalized. It only belongs to that module. And when you make a function static, it has the exact same effect, which means if I had 3 modules over here, and these 2 modules have static displays, and the third one has a regular display, and you had a prototype somewhere, the one that wasn't static will be picked up, because these 2 displays are only for the modules that they are built in. They cannot be externalized. They cannot have a prototype out there. We good? Okay. Then we talked about problems that they have the problems that have the solution within them. When we were learning in university a long time ago in the galaxy far, far away, we had a prof that used to say, like, if you want to write a recursive function, you have to first assume the function is already written and works properly. With that assumption, write the function. You follow what I'm saying? So I'm telling you, write a function that does this and that. Write a function that searches through an array. First, you have to think the search function is written, and it can search through an array. Then you have to say, if the array had only 1 element, I could say if the search is successful or not. If I cannot do that one, I'll give the rest for the search to do. That becomes recursive. So I'm using the function itself. It's not as easy. The concept is easy. The math theorem for it is easy, but doing it is not as easy. And the example was Hanoi thingy. We said to solve the Hanoi towers, we say that I want to sort n, move n rings on Hanoi towers. If it's 0, problem is solved. I'm not going to do anything. That's the end. If it's not 0, first I'm going to get n minus 1 of them and pass from A to B using C. Then move that one. Then pass from B to C using A. Done. Problem is solved. This will recursively solve the problem for me. How? By keeping the function calls alive. If we look at the factorial, and I'm going to simplify this factorial so we'll see, you'll see what it really means. So in here I'm going to say if I'm going to say if return else so this is a recursive function that finds factorial of a number. A factorial of a number mathematically means if you have function a number, it's the product of the number multiplied by all the numbers that comes before it, right? So now if I want to do the factorial of number 4, what happens over here? It comes inside. Now you can actually do this like a walkthrough, very simple walkthrough. How does it work? How does it work? You want me to do the walkthrough? So you see how it works quickly? Anyone? We are back in IPC 144. We are doing walkthroughs. Yes. We need image. Ah, there we go. Whoa, whoa. Scary. Okay. So now how if shoot. I can see the code over there, right? All right. So over there I have factorial that I want to do factorial 4, right? So what I do over here is this. I'm going to say in main factorial 4 is called. So I'm going to say over here factorial. This is the factorial function. Okay? And in fact, last time I've done this was, I don't know how many years ago. So I'm a little rusty. So this is the factorial function. Okay? And the factorial function receives an argument x over here, right? So I have received 4 in here. 4 is received. It comes in here is if x is greater than 2. Is it greater than 2? Is it? Okay, so what does it do? It calls factorial. So you're going to have the second call. So this is call number 1, call number 2. Call number 2 is factorial. And x over here is 3, correct? Then it goes to that one. So this is being executed. Is 3 greater than 2? Yes. Call number 3. This is factorial. Right? X. Now, what's going in? 2, right? Is 2 greater than 2? No, right? So what happens? It goes to next one. What does it do? It returns 2, correct? 2 returns where? To line 7, which is here. So now 2 is returned over here. Multiply by what? 3. So 6 is returned. 6 is returned over here, right? Multiply by what? 4. 24 is returned. Therefore, and this is the last one. Therefore, it's returned at line 15, and it's going to show what factorial of 4 is. So essentially, magic happens when it's like you're winding a toy, okay? And then you let it go, it's got doing like that and goes around, right? It's exactly the same thing. You keep winding it, winding, you keep calling it, and it returns, suddenly it does everything that it's supposed to do, okay? So this is, and that's why factorials are, recursive functions are extremely expensive. You have lots of heap, but you don't have enough stack. This is stack memory. If you call a function 50,000 times back to back, actually one of you did in your move assignment and in your copy assignment, you called the assignment operator in it. So it would have actually called the recursive thing. It would call it itself. It keeps calling itself until the stack is full and it crashes. So it is very expensive, okay? It is expensive, but coding is very small. If you want to code in legacy way, then you have to write a loop. But with this, it's just a return type, one-liner, okay? So good thing is that, good news or good thing, whatever you call it, is that you don't need to learn it. I may give you something like this, very simple to see if you can walk through it or not. Very simple, with 3 repetitions and things like that, to see if you understand what does it mean, recursion. But I will never ask you to develop a recursive algorithm for me. That is for DSA, okay? You don't do it. After factorial, we said, okay, now that we know all these functions, we can, we're going to introduce a new thing. When you have a small little function that is supposed to perform certain thing, and it's very tiny and little, and you only want to use it once, and you don't want to expose it to other things, you can write a lambda expression. A lambda expression is a short function that is defined and created inside another function. And when that function is gone, it's destroyed and it's gone. How do we create a lambda? With brackets. When you put brackets, we start a bracket, it means this is a function. So essentially, if you look at this, this is the syntax for it. When you look at it, it's just a function, but I wrote it in one line. You see, that's a function. So replace that bracket with a name, ABC. Then it becomes a function, right? That's literally what it is. That's the function. So bracket replaces the function name, parameter is the parameter, and then you have the function and you end it, whatever you want to do with it. And this is the function. I have 2 different functions over here. One of them receives something and the other one doesn't. And as you see, using auto, I can literally put this thing inside hello. But behind the scene, what happens is this. This lambda creates that temporary function and returns an address. Auto creates a function pointer and holds the address in there. And because hello is gone at the end, the function disappears after the main is gone. So makes it small to work with. That makes sense when you are doing the get int with those 2 is adult. So essentially, my is adult will be here. You see that? This is my is adult. It's a small function. No one else is going to use it. I just want to call my integer for an adult, and that's it. Ta-da. Now, this is object-oriented. Because you don't have another object-oriented, it doesn't violate object orientation. Because this function over here is a temporary variable inside your main, and it's gone. It's not going to be used by anyone else. It doesn't have any owner. It doesn't have anything. It just materializes in this logic, and it's gone. And the same thing for the other one. So essentially this becomes like this. Actually, when I write the lambdas like this, it makes more sense to me. It doesn't go that crazy. Are we okay down to this point? So,
I have a question.
yes.
When is this type of code ever needed?
What?
When is this type of code ever needed?
What is the what code that is needed?
This type of code.
Oh, when
Gonna be needed.
when the functionality, the function that you want is temporary, which means it's a logic that you're not going to reuse, and when it's small. I'll show you the future of it so you'll see exactly what I mean. But for now, just keep, let's keep that in mind, okay? So this is lambda in use. This is as far as we went last time. Okay, so we have, it's not going to be a short session. It's going to be right to the end, okay? So I'm going to put this in NBB today's session. I'm going to say A dash lambda in use. Okay, and meanwhile, let me open my cheat sheet. Now, those things I showed don't look at this. Okay, I thought that I'm going to start with that, but I'm not. Okay. So the one that I called you, it's called capture list. You see this thingy here now? Okay. That capture list, you see over here, the add over here is receiving a function, whatever. This capture list over here means my lambda can access neighboring variables by value. So when you have a capture list like that, okay, it means I can use k inside here without, as you see, this is my function, right? Oh, sorry, my bad. This is my lambda. Correct? Now, this lambda of mine can use k, the neighboring variables, by value. That's assignment. That's what assignment means. I'll bring everything over here with in detail. Don't worry. Give me 2 seconds. So capture by value. You can also capture the neighboring stuff by reference. So if you put ampersand inside capture list, it means it not only have access to it, but it can change its value. So if I do k++, the value in main k will change. It will change the value. This means capture everything by reference. Okay? These are the 2 main things. But now we call this a capture list, right? Capture list has these. So if it's only an assignment, it's capture everything by value. If it's only an ampersand, capture everything by reference. If you put an assignment, comma, ampersand x, it means capture everything by value, but x by reference. So there is a neighboring variable called x, and I want that be accessible to me. If you say ampersand and x, that means everything by reference but x by value when you don't put anything over there. Or you can add, I can say x by value, y by reference, not accessible anything else. Okay? Or I can do this. That means everything, oh, that's stupid just to write. Let me just write the other one. What I mean is that you don't need to, you don't have to write one thing. You can write as many as you want. I'm saying everything by value, capture x and y by reference. You okay? So you can literally write what you want. This, it means capture the current object. I can get everything from the current object. But anyways, so these are all the capture lists. I had something over here that I'm trying to find it to show you that, like, I literally call it a look into future. I think I put it in my cheat sheet over here. Yes. This is 3-4 weeks from now, this code. So I'm going to tell you there's an array. I want you to create an array and sort them, or create an array of whatever and sort them with this manner, whatever, okay? It could be as easy as this. Take a look. So I'm saying IO stream, I want vector, I want algorithms. These are all STL, standard template library. Vector is a fancy array. It's a very efficient array. Okay? So I'm saying create a vector of integers and put these values in it. Sort from the beginning of the vector to the end of the vector using that logic. Done. This is going to be fastest than anything you can imagine of. Even showing it like this, I can use an algorithm called for each that does faster loop than a regular loop. I can make this sort and ask this sort to be done to the number of cores of your CPU. So if you have 5 million things, it's going to sort them on 5 CPUs, 8 cores of CPUs, parallel, and then sort the last thing so it becomes faster. All these things is future. So that's why we are learning these. When you are using algorithms, what you want to do, how you want to insert your logic into the algorithm to do your stuff. That's what Lambda is for. Okay? Do I make sense now? Okay. Oh, you're going to learn lots of nice stuff when the time comes. What else I wanted to talk about? I want to play a game. So you guys are not playing. We have 1, 2, 3, 4, 5 rows over here, right? So the game is over here. I'm standing over here. I'm going to throw a ball. Okay, that's my thing. And the responsibility of row is like this. So row number 1 will catch any ball that is coming through. Row number 2 will get the volleyballs. Row number 3 will get the basketballs. And row number 4 will get the soccer balls. I'm not going to say football because that's like a torpedo, not a ball. But anyway, and the last one will, I don't know, golf balls, whatever. Okay. So now if I throw over here a basketball, who's going to get it? Row number 1. You guys are not going to get anything because I ordered it incorrectly. I put the ball first. If basketball is a ball, right? They're going to catch it. Volleyball is a ball. So it's wrong. I should have done it the other way. So I should say like row number 1 is going to get the soccer ball. Number 2 volleyball. Number 3 basketball. Number 4 is going to catch any type of ball that is coming. And last row, please, if anything passed, catch it. I don't know what. So if I throw this computer, the last one's going to catch it. Anything that is getting thrown, right? If I throw a volleyball, first row is going to catch it. Basketball, third row is going to catch it. Soccer ball, 4, volleyball, and so on and so forth. Are we okay with this? This is exactly the procedure we have for error handling in C++ called exception handling. Okay? So you literally write a code, and in this code you procrastinate. What do I mean by procrastinate? It means when you try to write a program and the file doesn't exist, what do? You say file doesn't exist, do this and that, ask again for the name of, and you keep interacting with the user, right? With exception handling, you procrastinate. What you do, you try to have the best possible solution for your application, and you put everything back to back. First open the file, then read the data, then search for the information, then print the results, then close the file. And you don't do any type of error handling in here. What you do, inside each of these procedures, if something goes wrong, you throw an error. At the end of all these procedures, you line up all the catchers. And you line up your errors from the most specific ones to the most general one, from volleyball and golf ball to any type of ball. And at the end, you say, anything else come, catch it. So what happens in your code, when you're actually writing code, when something goes wrong, you don't fix it. You just throw an exception. And you hope that the code is written for this exception to be caught back there. When you catch the exception, you handle it properly. Either you terminate your program after you handle it, or you go back to whatever you are doing. That's how it is. I'm going to show you the code. It's going to make sense because it is exactly as I explained it to you right now. Exactly. One important thing. Treat exceptions as what they are. What are exceptions? Exception. They are exceptional. The examples that I'm going to give you, they're all crap. Because I'm going to give you examples on, I don't know, error handling and checking for an integer to be valid. That's not what exception is for. Exception is more like the house is on fire, run away. It's not something that happens all the time. It's like, holy mother of, when you not have that feeling, that's the time for exception. Exception is that. Remember that. It's an expensive thing, and when I show it to you how it works, it's completely illogical. It goes completely out of the sequence of execution. And it's banana. Seriously, it's bananas. It is. I'll show it to you. So this is just syntax that I'm showing. This is like the worst type of code that I can write, but it shows how it works. So I have a function called throw double. Its job is to receive a double and throw it. Now what you throw can be any type. It could be a car, it could be a hospital, it could be a Xerox machine, it could be an integer, it could be a double. But hopefully if we are sane enough, we're going to include exception. an exception in the exception header file. There is a abstract. It's a base class created called exception that you can inherit from. Like we had the ball and then volleyball and a basketball and different things. It's the same thing that you can inherit from. So, but in here I'm just showing how things are happening. So I'm throwing. So these objects that I'm throwing, they have nothing to do with each other. There is no inheritance. I'm just showing syntax. In a try statement, you throw. If you throw something in outside of a try statement, program crashes, and crashes with unhandled exception. Or if you don't catch the exceptions that are thrown in here, and it reaches to the end of the program, program crashes, and the operating system says unhandled exception, yada, yada, yada. We're good? Now, let's walk through this. So in here comes I is 0. If I is 0, it says throw double, right? It goes to function throw double, it throws D. Is it valid? Yes, because the function was in try, therefore throw is valid. Throw can only be tried. You cannot throw anything outside of a try block. It throws. As soon as it throws, it comes down. The first catch is double, right? It starts from here. So from here, suddenly everything is skipped. You see the execution is here. Suddenly it skips everything and comes to line 21. It catches the double, prints this one, comes down to the loop, goes up, I becomes 2. Then it comes over here, I becomes 1. Comes over, it throws a constant character pointer. And as soon as it throws it, constant character pointer will catch it. And prints this thing. Comes up, I becomes 2. Then it comes over here, it's not 1, not 2. It's going to throw the integer. Did I catch an integer here? No. So the 3 dot is going to catch it. And tells me something was thrown that I don't know what it is. And then it goes up. And this line will never happen. Because if you have immediately something after a throw, essentially it's never going to get hit. Are we okay? Let's walk through it quickly and see how it works. And then we're going to go through the lecture for it. Whoops. Okay, so what is this? Oh, wait. Startup project. I ran the wrong thing. Can't change the solution very well. I'm not debugging. Startup project. Sorry, the other project was running. So it comes over here, and I have the string. Then it comes to throw double. It goes up to double, and now it says throw. Because it says throw, it jumps to cache. You see that? Catches the double, says double is here, goes up. Now it comes in here. It says throw a constant character pointer. So constant character pointer will be received. It's going to show it, and then goes up again. Now it comes to the third one. Throw I. Integer is caught. I cannot show the integer because 3 dots doesn't tell me what's coming in. I just know something is here that I couldn't catch. And now it says something is caught. Okay, and it goes out. That's how exception handling works. Okay, now let's actually take a look at it and see what's the story behind it. And as I mentioned to all my classes, many companies do not even use exception handling. They say we are not going to use exception handling, just if do the validation and return true false with a function, because that's more logical. But many other places do, so it's something that you need to know. So exception handling, error handling. Let me just talk about it. I just want to talk about error handling. Where is it? So again, the syntax, the basic syntax exception walkthrough. So the basic structure of an exception is this: try the code that may throw. When I say code, it means it could be a function that something is thrown in there, okay? And then catch, type ID, and so this is the syntax for it. And you can have many catches after that. Are we okay with this? So that's the basic syntax of exception. There are a series of standard exceptions. Series of standard exceptions. Okay, that they are all under the exception header file. Logic error, out of range error, runtime error, range error, overflow error, underflow error, bad cast. These are all exceptions that are already they already exist. You can throw them. Some of them can be thrown. Some of them are already thrown by the system. Some of them you have to create yourself. Like when you have, I don't know, a range error or overflow error, and these are not something that the system throws. You have to create an instance of it and throw it. But these are standard stuff that they exist. These are exceptions that they exist. For example, for bad allocation, if you include new, the memory allocation doesn't work like regular one, which means it's not going to return null if something goes wrong with the allocation. If something goes wrong, bad alloc will be actually thrown. Just remember that, okay? So if you ever see there is include new, you cannot say if p is equal to null bad memory. You can't do that. It actually switches to exception handling for it. Standard exceptions. No exception. Remember I told you I'm going to explain what is no exception when the time comes? This is the time now. Okay? So when you make a function no exception, it's not going to throw an exception outside of its own scope. So when you write over here, I don't know, G no exception, E can be called in it because the exception over here is handled already. It's safe. But over here, it terminates. So if you call H, H is calling F, which is throwing an exception, which is not handled. Therefore, it terminates it. Okay? So if you say no exception, it will terminate the function execution. It will not allow you to run it. Now, why we have no exception in move mechanisms, we put move. The reason is that when you make no exception for your move mechanism, it becomes safe. Therefore, all standard template library, when they can, they will move instead of copy. If you don't set your semantics, move semantics, to no exception, and you pass your objects to standard template library, even if you have move semantics, they're going to be copied because the standard template library thinks it's not safe. It may throw exception. So no exception, that's why no exception is a standard. You have to put it for your move side. Move, so the compiler prevents you if you have an unhandled exception over there. So you'll know what's going on. Okay? That's why we add no exception to move semantics. If your move semantics do not have exception, standard template library will copy them. It will not move them. Therefore, your program will run extremely slowly, okay, with lots of memory wasting and so on and so forth. Termination. How do we terminate our programs? At exit defines the destructor of your program. We have a destructor for an object, right? When you create a function, a void function, and pass its address to @exit, when program is getting terminated before going to the operating system, that function will be called. So essentially, you can set a destructor. If you have unfinished business before, if your program terminates prematurely, you can actually write that, call that thing and make sure everything is cleaned up. So that's like a, what should I call it? A destructor for your app, for your entire application. Okay? You can set it like that. Exit is literally return in main. Anywhere you do exit, you say I am terminating my application, and this is the code that is supposed to go back to the operating system. So it terminates it and will call @exit. Okay? But if you want to terminate, like emergency terminate, emergency termination is abort. When you say abort, no @exit will be called. It literally terminates your application. Poof. Okay? And goes back to operating system. That's what abort is. Okay? It literally terminates your application. So let's call this abnormal exits. So it sends signal abort and app terminates everything and terminates. It's called when we said exception escape, it means unhandled exceptions, okay, or handlers fail. So these are the abnormal terminations. Now, back to integer entry. Now, I want to create a smart integer. I want to have an integer that can read its own thing and validate itself the way it's supposed to. Okay, the first attempt of mine will be like the first program that I have written, which I had to change the name of the function as I would go through it. So essentially, Oh, I need to open the other one too. This is what I have. I have a validation that returns a Boolean. I have a get that returns an iStream reference, and a put that returns OStream, and I have them both overloaded. Just for show off, I did it trailing. Otherwise, there's absolutely no reason to do it, okay? This could be just regular functions, human being functions. Well, what is the thing about this is that the validation that I have, it's doing validation for a mark only. So the validation function that I have in my private section in int is called in get, and it does validation if the mark is valid or not. So I'm receiving the value if it's valid, and so on and so forth, right? So it's doing the validation over here. I'm not going through that foolproof thing. It's just a demonstration. We good? And says if it's not done, show the error message. If it's done, get out. So it shows the error message and so on. So that's the integer that I have. You can run all these things can be run. So you can run it later on at home and try it. But we learned how to use function pointers. And now that we learned that, we can actually write something better. So what I can do, instead of holding just a validation function, I can actually have a validation pointer to a function written, added as property to my integer, and by default set it to null pointer. What good does it do? The good thing is that in my logic, I can actually check to see if the validation function exists or not. If the validation function exists, I'm going to perform the validation. Other than if not, it's just a regular entry for any integer. So it not only enforces validation if I have it in my constructor. So in my constructor, if I actually say that I have the function, so if the second argument of my constructor is receiving the validation logic address, big thing so we can see, I don't have to write a comment. So it receives it. Now in my main, what I do, I write validation for whatever I want, and when I'm creating the validation, I'm going to say create valid, integer val, and my validation is validate age. So now when I do cin into my val, it's going to do an age validation. Now I can set my validation to be a valid mark. Now I do val, it's going to do mark validation. Whatever it's pointing to, it's going to do the validation for that. Or I can create 3 different integers, one for mark, one for age, one for whatever. Okay? And each one is going to validate. This is using pointer to functions that we don't like. Now let's move to the object orientation part. In object orientation, I actually create a validation module. In my validation module, I'm going to have a base class called validation, and anything that is supposed to do the validation is inherited from that. So my valid age is a child of validation. My valid mark is a child of validation. And they are all overloading the call operator that is a pure virtual. So they are forced to overload the call operator for a val and a string. So they have to overload this. Now in my validation.cpp, as you see, I am simply creating the operator for valid age to do an age validation, and for mark, I'm doing a mark validation and returning the result. So the function call operator is implemented based on what the class is. Therefore, in main, obviously in my integer, now what I have is a pointer to a validation function. Okay, I could have set it to null. Why didn't I set that to null? It's supposed to be null. So if I don't have a validation, I know it, but it's okay. So this, I'll do it like this. That's better. Okay, so now in my integer, the code is almost the same. So what I do in my getInt, I'm going to say if validation doesn't exist, call the validation function. But this one, because it's a pointer, I have to dereference it so I gain access to the object. Or I could have done this. I should have actually written it like this. It's a bad system, type way of writing it. I should have written it like this. Should I? Oh, no, 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 what are you doing? What are you doing? What are you doing? No, 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 my bad, my bad, my bad. No, 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 no. That's a completely different story. That's the next example. Forget it. This is good. So I dereference it and I put it like that. Anyways. So that's my validation, and it's called it based on what the validation is supposed to be. It's going to call it the way it's supposed to be called. So we are okay with that, and that's going to be my functor version of it. Again, please run it. Now, lambda actually goes back to my original thing with pointer to function that we said we don't like. So we can literally use the pointer to function version of the program but simply pass the lambdas to it. See, I'm saying mark. This is the lambda for it. And age, this is the lambda for it. So lambdas could be big, not small. If you're using it only once, that's the ugliest code I've ever seen in my life. But okay, like if you have have integer that works with pointer to functions, you can simply pass lambdas instead of creating things. Okay, so it's literally the function that I have written. I just copied it, removed the name, and put it over here so it became lambda. So that's with pointer to functions. And finally, oh, this is lambda with captures. Like if you want to count how many times you're doing it. So essentially, you capture it, and you can have number of tries in here. And you can add to the number of tries. So it tells you how many times you tried. You can use it with a capture to see how many times you do it. I explained how the capture works. And last, and probably worst, is the validation one with exception. So I'm saying bad integer exception is a child of exception, and there's a protected string message in it that says embedded integer, yada, yada, yada. All exceptions have a what that is actually implemented in it. So I implemented the what in my bad integer exception. When I go to my bad integer exception, this is what I see. What returns a constant character pointer. That's standard in the exception. So you have to implement the what in every exception that you are inheriting. So it returns the message's C string. So whatever message that I set in my bad exception, it's going to be passed over here. Now, for the rest, as you see, I'm just painting the ball in different ways. I am adding nothing else. I'm just creating different classes so I can capture them by type. Exactly the same thing like volleyball and basketball and soccer ball. They're all balls, but just different shape and different look. It's the same thing over here. I'm saying too young exception is bad integer exception. Nothing is implemented in there. The only thing that I implement in the constructor, I'm changing the error message. That's all. Too old exception, bad mark exception. So I go through everything and I set my different exception classes so they can be thrown. Now the thing is that in my in my integer now I'm going to procrastinate, which essentially means I'm going to say get it. If this happened, throw bad exception, bad integer exception. So it throws the bad integer exception, whatever it is. Now, because the bad integer exception is the father of those, depending on what I have in main, the exception that is thrown is fit to what it is. You see that? So this is valid age, valid mark. I pass it to age and mark, and I do a try and I read. If it's too young exception, do this. If it's too old exception, do that. If it's bad exception, do this, do that. And I could have had the 3 dots over here, but I didn't. Now, what you need to see over here is they call it separation of business logic and error handling. And that was a big hoopla about exception handling. They say in exception handling, you have the perfect logic with no error handling, and all the error handling is happening after. Therefore, you can see what you're doing. What is the correct process of the business logic going through? But that's that one. Please go through these codes at home and come back with question and tell me what the heck did you do over there. It doesn't work, and I will explain to you. Hopefully, everything's going to be good. Questions? All your quizzes are marked. But because we have people who joined the class late and they're doing it early next week, I'm going to release them then. Okay? So let me turn off the... log into the thing for an attendance. Let me do the attendance right now, and then we'll talk. Open up the attendance. Let me know when you're ready. And I can stop recording, actually.